All right, so a little Chem 50 review. All right. All right, so obviously we are going to do a lot of experiments in this class, and you've done experiments in previous classes. So I guess it's a good place to start as any is really with measurements. And when we do take measurements, remember that, as I talked about earlier today as well, you should always have a number and it should always have a unit associated with it, right? So you should never have just bare numbers. Units are really important because they do give a frame of reference for really what that number represents. You know, if you say you have, 100 and that's it, you're like, what do I have 100 of? You know, if you have 100 apples, that's very different than if you have $100. You can maybe buy 100 apples with $100, but those are different things. So units are really important. And when you do take measurements, in addition, it's really, really important that you take them to the proper number of digits. So let's talk a little bit about when we take measurements. For example, we had a ruler such as this guy here, and we want to measure something like this. So pretty much whenever we take a measurement, there's always going to be some degree of uncertainty within that measurement, some degree of estimation that has to occur. And really the degree of sort of uncertainty is going to rely upon the actual equipment itself. So typically when we look at anything, we usually want to figure out two of the markings that we see there. One is sometimes referred to as the large markings, and one is referred to as the small markings. Now, large markings, obviously in this case, that is 1 centimeter, that is 2 centimeters. So our big markings is really 1 centimeter. We usually want to look at the scaling and figure out how many of the small markings we have between those two. And when we start counting, by the way, we always start counting at the first marking. Can't really see that on that screen. Let's go with that color, maybe. Maybe that'll pop in. We usually start marking at the first marking past the last large one. So that'll be 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10 markings. That means in this case, we have 10 markings in between. Thank you. The large markings, each of the small markings in this case represents how much? 1 divided by 10 is, 0.1 centimeters, right? So each of the small markings represent 0.1. That'll be 1.1, 1.2, 1.3, 1.4, 1.5, 1.6, 1.7, 1.8, 1.9, and so forth. So whenever you do take a measurement, there should always be certain numbers that pretty much no matter who takes a peek at it, everybody should agree that it is at least that amount. In this particular case, everybody, I would think, should agree it is at least 1.4. So when we take a measurement, we do want to record those certain numbers. And those are, again, sometimes referred to as all the certain numbers. But now when we look at it, we can clearly see, it's not exactly 1.4. It's not exactly 1.5. And that's really where our estimation comes into play, our degree of estimation. And for example, I may think, well, maybe it's just a hair past the middle there. And maybe I think it's like a 6. And I would record, obviously, our units over there. And that 6 in my case would be what is sometimes referred to as the first uncertain number. And typically, when you do take a measurement, you should always record all the certain numbers plus the very first uncertain number. And really, when you do that, that is pretty much what everybody's favorite thing is. Those are really what the significant figures are. So this particular measurement would have how many significant figures? It would have 3 significant figures. Now, usually it's plus or minus 1 of that sort of last number where the uncertain number is. So basically what we're saying here is I think it's 1.46, but maybe it's 1.47, maybe it's like 1.45. It's somewhere in that ballpark as to where we think it is. Any questions on that there? Now, it's important to look at your scale because not all scales are really the same. So depending on the piece of equipment, you may see some different scales here. So if I take something like a graduated cylinder, and we do this here, and let's say we put some type of liquid in our graduated cylinder. We'll go with the green liquid. Why not? First off, when we do put a liquid into sort of a glass container, right, we typically will see the curvature of the liquid, right? And that is what is known as the meniscus. Curvature of the liquid is occurring because why? Yeah. So really what's happening, right, is the attractive forces between, say, like the water and the glass container are stronger than the attractive forces between water and itself. So what happens is on the side, it starts rising up because of that attraction. And we get that sort of meniscus that basically occurs, right? Cohesive, adhesive properties, right? And that is why, typically speaking, in a meniscus that looks like this, we always read from the bottom of the meniscus. And that's because that's really where, if we didn't have that attractive force, that's pretty much where the volume is actually at. So that's why we do read from the bottom of the meniscus. Most substances will give a meniscus that looks like a U. There are some meniscuses where the opposite is true. The actual substance itself is stronger attraction than the glass container, and it actually goes inverse, kind of goes upward. Mercury, for example, if you ever seen anything with mercury, which you probably haven't because they've taken out mercury out of all the labs, but mercury actually will go the opposite way. It will kind of be upside down, and that's because mercury is actually more attracted to itself than the walls of the container. So it kind of does the opposite thing. It comes in. And in that case, you would actually read from the top of the meniscus because it's basically heading in the opposite direction like that. So something like mercury, you would actually read from the top of the meniscus because the opposite effect's happening. So in this particular case, if we look at our big numbers here, our large markings between 10 and 20. So our large markings on this piece of equipment would be 10 milliliters. And that means our small markings, if we count, again, starting with the dash that happens after the 10 in this case. So 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. So once again, here we do have 10 markings between the two. That means each of the small markings represents how much in this case? 10 divided by 10 is? It is 1, I hope so. Yeah, so that is 1 milliliter. So this marking would be 11, that would be 12, that would be 13, that would be 14, that would be 15, 16, and so forth as you come up. So that means when we look at this, once again, here, if we read from the bottom of the meniscus in a badly drawn straight line, we would see that it is at least 14, right? Once again, that would be our certain numbers. And again, it's not exactly 14, not exactly 15. So we will make our estimate maybe 5 in this case with our units, and that would be our uncertain number. That means here, once again, this guy would have 3 significant figures, right? So again, all of them would be significant, with the uncertain number being obviously that last digit that we measured there, plus or minus 1. Now, in most cases, as you may be familiar with, you can typically take your reading to one more place to the right of the smallest marking. So in most cases, you basically could go one more place to the right of the smallest marking. Not in all cases. So for example, if we had something, say, like this, something like that. And we'll put our liquid right about there. So in this particular case, if we look at our large markings, once again, our large markings here is 10 milliliters. Now, if we count up our dashes between them, that is 1, that is 2, that is 3, that is 4, that is 5. Now, each small marking represents how much? It does represent 2 milliliters in this case, right? So that's a 12, a 14, a 16, and 18. Now, when we look at our liquid that's in there, it is actually between 16 and 18. The best you can do on this one is what's between 16 and 18? 17. Yeah, so 17 milliliters would be what you would record in this case. That number would have how many significant figures? It would have 2 significant figures. The uncertain number would be the 7, right? So it's like somewhere in there. The problem, obviously, in this particular case is you don't know really where 16 ends, right? And 17 begins. There's not enough room between those two to make that determination, as opposed to where it's just kind of like one difference between the markings. You could kind of split it up. So in most cases, you could go one more place to the right. Not necessary in every case, but you definitely always want to look at the scale, and it does. It is different depending on the scale that you use. Now, if I had something like, we went back to kind of like our first guide there. So we had our same sort of ruler here. And we were going to measure something that is like dead on that one. So in this particular case, as we saw earlier, our large markings is 1 centimeter. We do have our 10 markings here, which will give us our small ones at 0.1 centimeters. So this is 1.1, 1.2, 1.3. In this case, I can record 1.3 centimeters, 1.30 centimeters, 1.30000, because, more zeros makes it more scientific, right? So clearly that's too many zeros, yes, for this. Is there a difference between 1.3 and 1.30 in terms of how I record it? Yeah. There is a difference. Now, the difference, if you're not sure, is with this. We look at this particular number first off here, right? That basically would have how many significant figures? Would have 2 significant figures, which means our estimated digit would be which number? Would be the 3. So basically what you're saying is, I think it's 1.3, but maybe it's 1.4, maybe it's 1.2. And if you look at really what we're looking at here, it's nowhere near those numbers, right? So if we look at this particular number, how many significant figures would it have? Would have 3 significant figures. Yes, 0 would be significant there. The uncertain number would be that 0 in this case, right? And that means that we're saying, I think it's 1.30, but maybe it's 1.31, maybe it's 1.29. That is more realistically what we're actually seeing here on the actual scale that we're looking at. So you never ever want to lop off numbers when you're taking measurements, because in this particular case, we can take the measurement to 2 decimal places. You should take it and preserve that by putting a 0 there. If you take out the 0, although you do numerically have the same number, your measurement is pretty much crappier, much crappier than it should be in this particular case. That is a scientific word, I think. Yes. Any questions on that? So it's a very common mistake that people make. There's like right on the nose. We're just going to record the number and not worry about it. There is a way that you can figure out how far you could take the reading. If you're not sure, you basically take the smallest markings and divide it by 2, and that will tell you basically how far you take it. So if I take the smallest markings divided by 2, that's 0.05 centimeters. I should take it to the 2nd decimal place. If I look back at this one and take the smallest markings divided by 2, that's 1 milliliter. I should take it to the whole number. So if you're not sure, you can take the smallest markings divided by 2, and that typically will tell you how far you should take the reading to. Any questions on taking measurements there? There's 2 types of measurements that we take, right? One are come across our observations, I guess. one are qualitative, and one are quantitative. Qualitative is basically general options, general observations. Quantitative are basically measurements and numbers, right? So we do a lot of both, and in your notebook, you should record both types. You should record the qualitative, you know, it turned purple, it had rainbows, you know, it made a solid, whatever it may be. There were unicorns, you know. You should also obviously record the quantitative, any type of measurements that you make to the proper number of digits. Now, speaking of significant figures, let's actually talk about the rules just to make sure everybody's again on the same page. So the rules for sig figs is basically any non-zero number is significant. And by the way, when you're counting, you start left to right and you start counting as soon as you hit the very first non-zero. That's usually when you start counting your significant figures. So if I had 345, that would be 3 significant figures, as all 3 of them are significant. There are zeros, and these are sometimes the ones that give people sort of the hard time. And that is basically any leading zero are not significant. So 0.000347, this would have how many significant figures? We wouldn't count until we get to here, and then we would start counting, and then everybody else would be significant. So that would be 4 significant figures. If we have what are sometimes called trapped zeros, those are significant. So 403, this would have 3 significant figures, as the 0 is trapped between 2 non-zero numbers. So those would be significant. And then it's really the trailing zeros that give people a hard time. And if we have a 0 at the end, it may or may not be significant. What determines whether or not it's significant is there a decimal place in the number? Now, the decimal place doesn't need to be near the 0. It just needs to be actually in the number for it to be significant. So if I wrote 12,000 like that, it has how many significant figures? It has just 2, as there is no decimal place written. So these zeros at the end are not significant. And if I wrote 12,000 like that, they would then have, it would have 5 significant figures, as that decimal will now make all those zeros at the end significant. What is the uncertain number in this number here on the left? Which one's the uncertain number? It is the 2. Yeah, the 2 in this case is the uncertain number. The one on the right, the uncertain number is the last 0. Yeah. So the uncertain number in a measurement, or the estimated number in the measurement, is always not necessarily the last number, which is a lot of times it's the last significant figure. So the last significant figure that's written is really the one that is the estimated or uncertain digit when you take a measurement. Any questions on that there? The other really important thing, right, when we do calculations involving significant figures, you should follow the rules. The rules, by the way, are when we multiply or divide, your answer should have the same number of sig figs as the number with the least number of sig figs. So if I took 425 times 32, This number has 3 significant figures. This number has 2, which means we should end up with 2 significant figures in terms of our answer. Also applies to dividing as well. The other sort of operation we do, right, is adding and subtracting. Your answers should have the same number of decimal places as the number with the least number of decimal places. So if I took 3.456 plus 1.12 plus 3.4, try it without the calculator. That's like a 6, that's like a 7, that's like a 9, that's like a 7, I think. Yeah. In this case, I should take number 2, what? So we're going to look at decimal places. That has 3 decimal places, that has 2, and this has 1, which means technically we should go to 1 decimal place. We also would then need to do a little rounding action, and we should actually end up with 8.0 here as our number after we round. 8.0 has 1 decimal place, but how many significant figures? Has 2 significant figures. So that's important because sometimes we do a combination of stuff, right? We add and subtract, we multiply, we divide, all kind of together. So you do want to keep track of what you're doing. If you were, say, adding and then dividing, you obviously would do this part to decimal places, which would be 1 decimal place. And 1 decimal place in this case would get us something like 4.3, I think. Then we're dividing is the last thing we would do, right? Divide that number by that number, which means we then should transition to looking at significant figures. And that means really that's 2 divided by 2, which means we actually should end up with 2 significant figures here as our answers. So you want to keep track of it. Do you want to do a lot of rounding if you are doing multiple calculations in a row on the number? You should not do a lot of rounding right until the very end and kind of clean it up to the right number of significant figures. But you should keep track of them throughout your calculation. But you definitely don't want to do a lot of rounding to the end. Any questions on that there? Speaking of rounding, we should always give things to the proper number of sig figs, right? Really try to do that. But you shouldn't do any kind of extreme rounding, right? Or anything of that craziness. Like if I had 13,333 and I wanted 2 sig figs, what is it? So 13,000, 1.3 times 10 to the 4. Which ones are acceptable here? Well, we'll just look at these 2 for now. How many sig figs does that have? All right. Now, if I owed you $13,333 and said, I'm going to pay you 2 significant figures, here's $13. Not going to make it out of the room, even though you look friendly out there. Probably not, right? So although it does have the right number of significant figures, there is a very big difference in the meaning of those 2 numbers. So you never want to super round to get the right sig figs, but change the meaning of it. Now, if I give you $13,000, maybe I get the $333 teacher discount. It's about the same value in terms of the number and stuff like that. So you should never change the meaning of a number by doing rounding. This is obviously scientific notation, right? By the way, this would have how many significant figures? It would be 2 when you write a number in scientific notation, right? All the numbers before the times 10 part are significant. And sometimes that is the only way to get a number to the right number of sig figs is to write it in scientific notation. Speaking of scientific notation, just to make sure we know how to properly do that. When you write scientific notation, should be n times 10 to the n. This is a number between 1 and 10. That means it is not a number less than 1. It is not a number of 10 and above. It's got to be like between like 1 and 9 point something to be proper scientific notation. This is a positive or negative number, depending on which way you move the decimal. So again, if we had 325 here, we would go 1, 2 places, 3.25 times 10 to the 2. You should never lose significant figures as well when you move into scientific notation. This has 3 significant figures. This number also has 3 significant figures. So you never want to lose any significant figures when you do that or move a number into scientific notation. Do you have to give all your answers in scientific notation? The answer is no, you do not. But you do need to sort of give your numbers the right number, sig, fig. So however you want to do that, if you want to use scientific notation, you can, but you don't necessarily have to use it. More importantly, and what I find most people don't really know how to actually use scientific notation on their calculator. So let's talk a little bit about calculators and scientific notation to make sure that you know how to punch those in correctly, because we will definitely be doing that. So on your calculator, your scientific calculator, you should actually have an exponent button. It should be the EE button. It should maybe be an EXP button. Or if you have some of the newer two-tone type calculators where it's kind of like white on the outside and maybe blue or green, mainly overall, you may actually have a times 10 to the end. And usually if you have that calculator, you also have like a wheel on it. It looks something like that. So those are really your exponent buttons. If you've been putting numbers in your calculator, scientific notation, using something like shift and the log button or the caret button, the multiplication button, you are doing that wrong, and you will find yourself with the wrong answer in this part of the deal. So for example, if I wanted to do 6.17 times 10 to the minus 4 and actually punch that into my calculator correctly, I would go with 6.1. I would hit my exponent button. Now, on a lot of people's calculators, if you hit that button or that button, it will do one of these two things. 6.17, put an E. Might go 6.17, pop up a couple of zeros. Maybe it'll even say times 10 on the bottom, something like that. At that point, you then should move the rest of the part here. When you hit the exponent button, it represents this part of the number. So that is really what the exponent button represents. That means you do not need to use the multiplication button or anything like that. What is left is the -4. Also a problem for some people. You actually have a negative button. Usually it looks like this or like this. It is not the subtract button. Yeah, so you do need to use one of those. You hit your negative button. It will then put a negative up. And then you hit 4, it will go 4, it will change this guy to a 4. And that would be the proper way to punch a number in scientific notation into your calculator. Now, if you have, say, this calculator here, or you have really these buttons here, you basically do the same thing, except that the way that those calculators are typically programmed, you have to put parentheses around all the numbers. Otherwise, you're going to get the wrong math done. So you would need to open a parentheses, hit 6.17, and then hit your exponent button. And it would display something like this, 6.17 times 10 to the blinking cursor up there, up on top. At that point, you would then hit your negative button and 4. And what it will do is it'll look something like this. The problem, though, is your blinking button will still be up on top. And that's where the wheel comes into play. You hit that, it will bring your little cursor down so you could close the parentheses. Otherwise, if you do not bring the blinker down, you will have like -4 and a little small parentheses on that side, and you'll usually get an error. So if you do have sort of one of those kind of newer ones with two-tone, white on the outside, blue on the inside, the only difference is you got to do the parentheses, kind of a couple extra button pushes But you do need to make sure that you know how to properly do this. Otherwise, you will be in trouble. There's a lot of numbers that you need to put in there and calculate. Any questions on your exponent button? Yeah. If you're not sure where your calculator's exponent button is, just come see me. We'll find it, but we will definitely be using that a lot throughout the semester. You usually will know that you're not putting numbers in correctly, and when you're doing a math problem is you'll get the answer. The front part of the number will look good. The exponent part will be just like slightly off by 1 or something like that. So that's usually an indication that you're not punching it in correctly. Any questions on scientific notation and your calculator? Now, the other thing when we do take measurements and stuff like that, we look at a couple of things like accuracy versus precision. Right. Accuracy is how close you are to the true value. Precision is how close a set of numbers are to each other. So, for example, a classic example, the bullseye, right? The goal there is to hit the bullseye in the middle. I throw my darts. I missed it. That's all right. Am I accurate? Am I precise? I am not. I'm neither in that case, right? So I go, well, we'll go double or nothing. I pick up my pride and my darts here. Try that again. And I throw my darts again at the board and I hit. Am I accurate? No. Am I precise? I'm precisely not accurate, right? So you could do something the same way a bunch of times. It could be wrong every time you do it, but you do it the same way. So you can be very precise in how you do something, but you may not be accurate, right? And so I say, well, I'll triple or nothing you and all that good stuff. We'll take my darts back up here. And I throw them again. And I hit here. Am I accurate? Am I precise? Right. So that's really the goal when you're doing experiments or taking measurements, right? You want to be accurate and you also want to be precise. That's why a lot of times when we do experiments, right, we do multiple trials, right? So when we look at precision, it helps us understand, is a experiment reproducible, right? You do multiple trials, get the same result every time you do it. You know, you are very reproducible and stuff like that. Accuracy and being accurate tells us, you know, how close we are to what it should be. Any questions on any of that measurement type stuff? Okay. Another important thing to keep in mind is hopefully molar mass, right? Molar mass. Units of molar mass are grams per mole, right? So the molar mass is grams per mole. We could get the molar mass from our friend, the periodic table, if we wanted to. Do a little lithium, 6.941. It is a number on the bottom, right? That's the atomic mass in atomic mass units. And AMU is equivalent to molar mass, which are grams per mole. And we could say that that is 6.941 grams of lithium in 1 mole of lithium. And basically the molar mass, 6.941 grams per mole. We could also look at lithium, our molar mass, as a conversion factor. It is the conversion factor that lets us go from grams to moles, right? And moles to grams, which is something that we do a lot as well. So for example, if I had 32.6 grams of lithium, and I want to know how many moles that is, I could use the molar mass as a conversion factor, right? Conversion factor is 6.941 grams over a mole, or a mole is 6.941 grams. Those are two conversion factors. The way we show a lot of calculations in chemistry is through what is known as dimensional analysis, right? That is where you show the units canceling out in sort of a fraction sort of deal. So we could take 32.6 grams of lithium, and when you do dimensional analysis, opposites cancel. So since grams are on top, we could use the grams on the bottom, 6.941 grams per mole of lithium. Grams will cancel because you're essentially dividing grams divided by grams. So same idea, if you divide 4 divided by 4, it ends up being 1. So the units cancel. We end up with 32.6 divided by 6.941. Gets us 4.70 moles of lithium in this case. First off, any question on that calculation? Yeah. By the way, there are certain numbers which are measurements, right? And there are certain numbers which are exact numbers, right? Exact numbers are things that are either counted or they are definitions, kind of like that, 6.941 grams per mole. So in terms of sig figs, we would look at that. That is 3. And by the way, math here, we're multiplying the top and dividing the bottom, right? Is mathematically what we are doing in this case. And that would give us our answer that has 3 significant figures when you do it. You should show your work this way with dimensional analysis, the units and things canceling. Any questions on that there? Now, if we had or wanted to figure out something that is obviously more than just one element, we basically just add up everything. So if we had something like CO2 and we wanted the molar mass of it, we would go to the periodic table, find carbon, 12.01. We would find oxygen, which is 16. When we do pull the molar mass off the periodic table, we usually go to about 4 significant figures when we do so. That would give us 12.01 grams per mole plus 2 times 16 grams per mole. Gonna give us 4401 grams per mole would be our molar mass of our CO2. So we could do it for anything as well. You just basically add up all the parts to do that. We don't use it all that much in this class, but you might also remember your friend Avogadro and his number, right? That is 6.022 times 10 to the 23. And that means 1 mole of anything, right, is equal to 6.022 times 10 to the 23. And these could be atoms, they could be molecules, right, and so forth. We use Avogadro's number to do that, to go from moles to atoms or molecules. And backwards, if you have atoms or molecules, you could get moles, right? So remember, don't use Avogadro's number in any other situation. Really, if it mentions something about atoms or molecules, then you should use it. If there's no mention of atoms or molecules or anything like that, then you obviously do not need to use it. Any question on that there? Now, speaking of which, what is the difference between like a molecule and a compound? Is there a difference? What's the definition of a molecule? Definition of a molecule is 2 or more atoms, yeah, together. Definition of a compound is, yeah, you need at least 2 or more different atoms, right? Of elements, right? So 2 or more atoms of different elements, I guess is a better way to put that. 2 or more atoms of different elements that work. So H2O, right? That is a molecule because it has at least 2 atoms. It's also a compound. Is it an element? It is not an element, right? Now, there are certain elements that are molecules, right? There's a bunch of them, which like H2, O2, N2, all your halogens, basically, F2, Cl2, Br2, I2, right? All of those guys are elements because they only contain the same element, but they're all diatomic molecules, right? Because that is how they come. They come basically as twos. Any questions on that there? All right, then let's talk a little bit about equations and reactions, which is a really important part. First off, in a chemical equation, on the left-hand side of the arrow are our reactants, right? That's our starting material. On the right-hand side are our products, which are obviously the things that are formed as a result of a chemical reaction. On top of the arrow, sometimes things are written like this. These are sometimes what are referred to as a catalyst. As we'll actually talk about, a catalyst is not a reactant, it's not a product. It doesn't get used up in a chemical reaction. It is there basically just to facilitate the reaction, and in most cases occurring quicker. So a lot of times catalysts will be written up on top of the arrow. Other things that we see in chemical equations are states, right? Like solid, liquid, gas, aqueous, right? Aqueous is a water environment typically. Is there a difference between liquid and aqueous? The answer is yes. Something that has the liquid designation is a pure liquid, a pure substance, like water itself. Yes, is a pure liquid. If I take water and like you're going to do next time and take some solid sodium chloride, which is a salt, right? The salt will dissolve in the water and it will make a sodium chloride solution that gets the aqueous symbol. So aqueous basically are solutions. Solutions are homogeneous mixtures, right? They are things that look the same throughout. So everything dissolves. And that's basically what a homogeneous mixture is. So if you see the aqueous, that usually means you took something, you dissolved it in something that's really the solvent, and you made a solution. Anything that has the L is obviously just a pure substance by itself. It's really important when we do have an equation that we always make sure that it is balanced, right? So you always want to make sure that your equation is balanced. Otherwise, it's kind of useless for you. So, you know, if you had something like H2 plus N2 makes a little NH3. The idea of balancing here is we would put coefficients in front of all those guys to make sure we have the same amount on both sides. And in this case, we would have 6 hydrogens on the left, 6 on the right, 2 nitrogen on the left, and 2 on the right. Idea behind that is the law of conservation of mass, right? We don't create nor destroy anything. What actually happens in a chemical reaction? What's really the only thing that's happening in a chemical reaction? What gets broken? Bonds, yeah. So basically all the bonds get broken. So just the electrons, the bonds. So we break apart all the bonds and then they reform. Perhaps you remember energy diagram as they're going up to the transition state and down. But that's because that's all that happens. We have the conservation of elements, right? We don't create elements or destroy elements. They just sort of rearrange in a traditional chemical reaction. In a nuclear reaction, not so much. We'll talk about it later on in the semester, but in a chemical reaction, it's just breaking and making bonds. By the way, out of protons, electrons, and neutrons, which one is the most important in terms of what element we're dealing with? Yeah, that's a 1 out of 3 shot there. It's like a 33 1/3. It is the protons, yeah. Protons is the atomic number, right? Which is the other number that you see on the periodic table. Protons, which is the atomic number, that's the number up on top. And that is how many protons there are. And everybody has its own atomic number and number of protons. So that's what determines, you know, what element you're dealing with. That's also why in a chemical reaction that only involves electrons, we never change the element because nothing happens in the nucleus where those guys are hanging out. So we always change only the coefficients. We never change any of the subscripts or anything like that because obviously that would change what it is. This is really important when we do a little stoichiometry, right? Everybody's favorites, right? From the equation, or not, maybe not, I don't know. From the equation, we could look at these coefficients as the moles of each of these things, right? So we could do a little 3 moles of H2 react with 1 mole of N2. We could do 3 moles of H2 will produce 2 moles of NH3. 1 mole of N2 will give you 2 moles of NH3. So these are all what are referred to as being stoichiometric equalities that we could get from the balanced equation. We could actually write 2 conversion factors for them. So for example, if we want to know, we started with 42 grams of H2, you know, how many moles of NH3 that would be. We can take our H2 and convert it to moles. So we would take 42 grams of H2, use the molar mass from the periodic table, 2 times 1.008 grams per mole of H2. And that would get you 42 divided by 2, gets you something like 20.833. I'll take it to a few digits. Moles of H2. That is where the stoichiometry would come into play, right? The mole to mole relationship between these two. And we would do a little on the bottom to get rid of the H2. 3 moles of H2 gives us 2 moles of NH3. So we would divide that by 3 and times it by 2 gets us, we'll call it 14 moles of NH3. Obviously, in this case, if we wanted to know how many grams that would be, we could use the molar mass of NH3 and convert that into grams, which is, again, a common thing that we do. Questions on that there? Now, you might also remember that there are limiting reagents, right? Or some people call them reactants, whatever you like to call them. What is the deal with limiting reagents and excess reagents? In every reaction, right, there's always some reactant that gets used up first, right? And that is known as your limiting reagent. And in every reaction, there's always one that you have plenty of, which is known as your excess reagent. And the importance of limiting reagents are, if we have just a simple explanation, if I have A plus B making AB, the only way to make products is to put A and B together. So if I run out of A, I would no longer be able to make any more product. So it's always the limiting reagent that is the one that determines how much product that you would make. And to solve that, there's multiple ways to solve it, depending on whoever you had. One common way a lot of people teach is just to do 2 separate stoichiometry calculations using the starting amount of each reactant, and whichever one produces the least amount of product would be your limiting reagent and your theoretical yield. Is that how most were taught? Yeah. Some do a calculation where you take both reactants and figure out how much of one you need to use up all the other. And if you have enough or don't have enough, that's another way to do it. So there's multiple ways you could do that. But if it is a limiting reagent situation, that is always the one that determines really how much product that you would make. Any questions on that? So really important to be able to write equations in this class, be able to balance them, obviously. And also important is to remember the different types of reactions that you learned about. As you might remember, when we talk about types of reactions, there's really 2 big categories of reactions that you deal with. The 2 sort of categories of reactions are double displacement reactions and redox reactions. So pretty much all reactions will fall under one of those 2 categories. Either it's really a double displacement reaction taking place, or it's a redox reaction taking place. So let's just talk about a couple of these here to make sure. In terms of double displacement reactions, they have a general form of AB plus CD. The way you know this is a double displacement reaction is those are two ionic compounds. Ions are things that have charges, right? There are cations that are positively charged. There are anions that are negatively charged. And in chemistry, what two things like each other? Things that are oppositely charged, right? So positive, negative things are attracted to one another. Things that have the similar charge repel one another. So what happens here is basically the two positive guys will switch partners. And on the other side, you will form two new ionic compounds. And that is your classic double displacement reaction. Now, underneath sort of the big category of double displacement reactions, there are reactions which are referred to as precipitation reactions. And in a precipitation reaction, a solid or a precipitate if formed, sometimes abbreviated as a PPT. That means when you do this double displacement reaction, one of these ionic compounds will form a solid. And that is based on solubility rules. We remember those, hopefully. Right, like all nitrates are soluble, right? Chlorides, bromides, iodides, all those guys are soluble in everything except for silver, lead, and mercury. So all those sort of rules that hopefully you know, things in group 1 are soluble and everything. So based on solubility rules, when you do this sort of double exchange, one of those guys may form a precipitate, and that's known as a precipitation reaction. The other sort of classification that falls under double displacement reaction are acid-base reactions. And in an acid-base reaction, we take an acid plus a base, and we make a salt and water. A salt is an ionic compound, so some type of positive, negative guy, and obviously water is H2O. We have many big chapter devoted to nothing but acid and base type reactions. So being able to write those are really, really important. But they really are double displacement reactions, these acid base ones. When you do the double displacement part of it, it basically will make water. One of the three reasons why a reaction takes place are what? Reaction will take place because you want to make a solid, which is a precipitation reaction. You want to make water, which is an acid-base reaction. The third reason a reaction takes place is an electron transfer, which are redox reactions. So those are really the three reasons why a reaction takes place. One of those three things happen, and that are accounted for these different types of reactions. So for example, if we take something like hydrochloric acid, which is HCl plus a little sodium hydroxide, that is a strong acid. That is a strong base. That is a plus minus guy, plus minus. So when these guys switch partners, they do this move, and that is going to give us our water and our salt, which in this case is sodium chloride. Yeah. So that's our water and our salt. So this is an example of a acid-base reaction, neutralization reaction, they're sometimes called. But it really is just in the heart of it a double displacement reaction. The cation for all acids are H+, right? H+ is basically what makes something an acid. This equation, like we wrote it here, is what is known as the molecular equation. You could also write an equation that really displays what's going on in this reaction. And because hydrochloric acid is a strong acid, it's a strong electrolyte. Strong electrolytes mean they do what? They do conduct electricity, and they 100% break apart in solution into ions. So we could write something like H plus Cl minus, which is what that strong electrolyte would do. Sodium hydroxide, which is a strong base, would do the same thing, break apart completely in solution. Something like water that's a pure liquid will actually stay together. Anything that's a liquid, a gas, or a solid will stay together in solution. And something like sodium chloride, which is also a strong electrolyte, will break apart into sodium and chloride. This equation here is what is sometimes referred to as the total ionic equation, or some people call it the complete ionic equation. And this really represents what is going on in this particular reaction in the actual beaker or whatever. You basically have all these ions floating around basically in that beaker. When you write the total ionic equation, you should be able to look on both sides of the arrow and find some ions that look exactly the same. So in this case, sodium and chloride. These are what are known as spectator ions. And if you are a spectator, you typically are just watching what's going on. So they're there to balance out the charge. They're not really being involved in the formation of any product. They're just kind of there hanging out. And typically with spectator ions, we could get rid of them. And what that leaves us is the third type of equation, which is important and we will use in this class as well. All three of these, H plus OH minus makes some water. And this is what is sometimes referred to as the net ionic equation. The net ionic equation pretty much cuts it down to the heart of the matter. This is exactly what's happening in this reaction. And as you can see there, it is the formation of water, which is really what's happening here. And that is, again, one of the driving forces for why a chemical reaction takes place. So being able to write the equation up on top, being able to think about total ionic and net ionic equation are things that we will do in this class. And you need to be able to do those things. Any questions on that there? Now, under the double displacement umbrella, those are really the two types of reactions, your precipitation reaction and your acid-base reaction. Now, all other reactions pretty much fall under that redox category. Redox means oxidation and reduction reactions. And when something is oxidized, it will lose electrons. And when something it goes through reduction, it will gain electrons, are two definitions of it. Sometimes people remember it as Leo the lion goes grr. Loss of electrons, oxidation. Gaining of electrons, reduction. Some people like the oil rig. Oxidizing is losing, reducing is gaining. You could choose either one. It doesn't really matter. But those are two definitions. There's some other definitions of oxidation reduction. Sometimes in organic chemistry, for example, we look at either did somebody gain oxygen as they went from reactants to products, then they would be oxidized. Did they lose oxygen as they went from reactants to products, then they would be reduced. And also we look at hydrogen as well. If somebody gained hydrogen, they were reduced. If somebody lost hydrogen going from reactants to products, they were oxidized. When we lose electrons, do we become more negative or more positive? We become more positive, like cations, right? Because when we lose electrons, we have more positively charged protons. So we're more positive. When we gain electrons, we become more negative. So one way, easy way to sort of figure out, is something going through oxidation or reduction, is just to think about a normal sort of number line. And if somebody, in terms of their oxidation state or their charge, which is a little bit different, if they started out in one place and then ended up becoming more positive in terms of their oxidation state, that guy would go through oxidation. And if somebody went the opposite way, became more negative, they would go through reduction. So again, you could look at something, their oxidation state on one side or the other to determine that. And we'll talk more about that when we get into the sort of redox chapter a little bit later on. But underneath the redox sort of category of reactions pretty much follows everybody else. You have your synthesis, our combination reaction, and that is when two things make one, basically, and they come together. So like H2 plus O2 makes some water. Two things make one thing is a synthesis or combination. A decomposition is another one. Decomposition reaction is where one thing breaks apart into two or more things. So if you run an electrical current through water, you could break it back into its hydrogen gas and oxygen gas. So one thing makes two. Also falling under redox reactions are single replacement reactions. A plus B, C. And in this case, this is something that has no charge. It could be a metal or a non-metal. And this guy is an ionic compound. And if it is a metal, what will happen is the metal will come in and kick out the positive guy and make a new ionic compound. And we'll get the metal coming out with no charge. You could also do this with non-metals. This guy was a non-metal. It would come in and kick out the negatively charged guy, and we would make, again, a new ionic compound that looks something like this. So something like zinc plus some hydrochloric acid. You've probably done this at some point. This has no charge. By the way, any element or anybody from the periodic table that is not combined with anybody else does not have a charge. So things only get charges when metals and non-metals come together. So anybody by themselves has no charge. Hydrochloric acid is positive, negative. So what's going to happen here is the zinc, when it does get a charge, it's going to be positive. Going to kick out the hydrogen, going to make hydrogen gas in that case, and we'll make some zinc chloride. A little balancing action there. You'll see some bubbles and stuff like that. This guy goes from 0. This guy then becomes +2 at that point, and the chloride is -1, by the way. So if we look at this, we could use our little table up here on top to figure out who is being oxidized. Zinc went from 0 on the left to +2. So if we started at 0 and then ended up +2, it is definitely being oxidized, right? So it's losing electrons. It is actually the hydrogen here that started at +1. And the hydrogen over here in this natural state has no charge to 0. It's actually being reduced. It's gaining electrons as we go to the left in that case. So it's the hydrogen. The chloride here is actually doing nothing. It's a spectator ion. You actually could write a net ionic equation for that reaction. That looks something like this, where you will see that happen. Not 2 plus H2. Throw an extra 2 in for free, I think, here. That was where I wanted to put my 2. So if we broke this apart into our total ionic equation, it will look like this. That 2 gets distributed to our hydrochloric acid, to each of them. This will break apart. This 2 will come to the front here, and the H2 will stay together because it's a gas. Our spectator ions actually are chloride here. That leaves us our net ionic equation that looks something like this. That shows the redox part of it. Where this guy's going from 0 to +2, basically +1 to 0 in terms of their oxidation states. So sometimes we use net ionic equations with single replacement reactions as well. Any questions on that there? Now, the last one that sort of falls under the combustion, the redox umbrella is combustion reaction. Most people think about the organic combustion reaction, organic guy, which is basically carbons, hydrogens, or oxygens, plus some O2 makes CO2 and water. That's like when you light your Bunsen burner, that's methane. And you basically will produce CO2 and water. The basic definition, though, of combustion is any reaction that actually just has oxygen involved. So technically, any reaction that involves oxygen is a combustion reaction, where if you had something like this, this is a combustion reaction technically because it has oxygen. It is also a synthesis reaction because two things make one. So something that you might be familiar with is there are multiple ways you could classify the same reaction depending on what you're looking at. Any question on reactions, types of reactions? Being able to write the equation and the reaction is extremely important, and you need to be able to do that in this class. And you need to do it on exams and stuff is considered part of the work that you need to show. So you can't just do the math or fake the math like a lot of people try to do without writing the equations. You got to be able to do those things. Any questions on those things there? All right, so last thing we're going to kind of talk about here to finish up on that's relevant are solutions. And solutions, right? There's two parts to a solution. Solutions are homogeneous mixtures. There is the solute and the solvent when we talk about a solution. The solute is the smaller part of the solution. The solvent is the larger part of the solution. When you put both of those together, that makes a solution. And again, solutions are typically the ones that get the aqueous symbol next to them. When we talk about solutions, usually we talk about concentration, and probably the most important concentration unit we use is big M, which is molarity, right? And molarity is equal to moles of solute, liters of solution. So molarity basically is moles per liter. You can think of it as a formula. If you need to solve for liters, that is moles divided by the molarity. And if you need moles, which is a common thing, that is liters times molarity. So if you do have something that is 3.65 molar sodium chloride and you're doing a calculation, it is highly recommended that you get rid of the big M and convert it into a conversion factor where you see both units. And that would mean that there would be 3.65 moles of sodium chloride in a liter. And you can use it like a conversion factor and do dimensional analysis. Liter up on top, 3.65 moles of sodium chloride. So if you leave the big M and you do your calculation, it's very common that people will not know where the volume part is, and they just think moles, and they kind of screw up the calculation. So really important to kind of do that. We will definitely use this a lot in our class here and being able to do that. So obviously, if I had 45 milliliters of a solution, I want to know how many moles that was. We would have to do a couple of things. Again, we would turn this into a useful conversion factor, moles per liter of sodium chloride. Now my 45 milliliters, I do need to convert into liters for everything to work out correctly. So 45 milliliters, there's 1,000 milliliters in a liter. That is definitely a conversion we use a lot. Those guys will cancel. We're basically going to get 0.045 liters, right? Now that we have that, we could use our molarity like a conversion factor, 3.65 moles of sodium chloride per liter. Once again, multiplying that out and dividing, the liters would cancel. And in this case, 0.045 times 3.65 would get us something like 0.16 moles of sodium chloride in this case. So these are very common sort of calculations. Whenever you use molarity by itself, the volume always has to be in liters for everything to cancel out correctly. Because if you multiply milliliters times molarity, do you get moles? You do not. You get what are known as millimoles. Yeah, so you'll be off by a factor. It's okay as long as you do everything in milliliters, but you'll actually get millimoles. Any questions on that there? So the other important thing is when we use solutions is dilution. Dilution is when we basically add more solvent, right, to a solution. The reason that affects the molarity is because it's per liter of solution. When we add more solvent, we're increasing the bottom number here. That means the molarity goes down. So that's an M1 V1 equals M2 V2 situation. Molarity and volume equals molarity and volume. Or some people are taught C1 V1 equals C2 V2, same deal. That's just generic concentration, volume, and stuff like that. Typically, these are the more concentrated solutions. These are the more dilute solutions. So if I had a 19 molar sodium hydroxide solution and I wanted to make 250 milliliters of a 0.55 molar sodium hydroxide solution, I would put it into my equation. 19 molar would be my M1. V1, I don't know. M2 would be 0.55 molar. And my total volume would be 250 milliliters. And in this case of my made up example here, we will end up with about V1 equals 7 we'll call it 2 milliliters. In this case, I'm dividing, right, this to the other side. It is okay in this case to leave this in milliliters, and that is because when I multiply these two, I get millimoles. When I divide out by the molarity, they cancel, and I'm left with milliliters. So the only place where it's okay to leave it in milliliters, the volume, and use molarity is when you're doing a dilution problem, because the units cancel out and everything works out okay. By the way, if I were to make the solution, would I take 7.2 milliliters of my sodium hydroxide, which is the 19 molar guy, right? I would take it out of the bottle. I would put that into here, my 19 molar stuff, my 7.2 milliliters. Would I put another 250 milliliters of water in there? I wouldn't, otherwise my total volume would be incorrect, right? So to figure out how much water I would need, V2 minus V1 is typically what you do. And that tells you how much water I should put in there to get me to the proper volume when it's all said and done. Question on dilutions, molarity, we use it a lot. You need to be able to do those things. One last thing here, let's say we were going to make in a test tube, wonderfully drawn test tube there. Let's say we had a table and a chart. And let's say we had 0.25 molar sodium chloride. Let's say we had 0.005 molar, I don't know, silver nitrate. Bad choice, but I will go with it. Maybe not silver. Let's do sodium nitrate. We'll do both. And let's just say we had just some deionized water, right? And let's say we used 5 milliliters of this guy in test tube number 1. Let's say we used 4 milliliters of this guy. Let's say we use 1 milliliter of this guy, right? So I'm going to do that. I'm going to throw into here my 5 milliliters of my sodium chloride. I'm going to throw in there my 4 milliliters of my sodium nitrate. And then I'm going to throw in there my 1 milliliter, not drawn the scale, of deionized water. Yeah. All right. In test tube number 1, the molarity of the sodium chloride, is it 0.25 molar? We got very quiet. That's a yes or no answer. Yes, no. The molarity of the sodium nitrate, is it 0.005 molar? I'm not here alone, right? All right, I just want to make sure. All right, so let's talk about it. The answer is actually no, it is not in the test tube, right? Because what happens when we put all these in the test tube and we do a little mixy, shaky, maybe not so much shaky, maybe just a little mixy. I am now doing what with all those solutions? Each of those solutions have now just been diluted. Yes, they all been diluted, right? The total volume of everything just changed, which means in order to figure out the molarity of the sodium chloride in that solution or the sodium nitrate in that solution, I need to do an M1V1 equals M2V2. So for example, for my sodium chloride, my M1 would be 0.25 molar. My V1 would be 5 milliliters. That's how much I used of it. My M2 would be the new concentration inside my solution. The V2 would be my total volume, which in this case is 5, 4, and 1, which would be 10 milliliters. So when I solve for M2, that it will actually give me the correct concentration of my sodium chloride in the test tube when it's mixed together. That is something we do a lot. We put a lot of stuff into test tubes, we mix them together. You need the correct concentration. So it really is a dilution that's going on in that case. Question on that there. All right, so overall, if it's been a while for some of this stuff or none of this looks familiar to you, which I hope is not the case, we really do a lot with solutions, molarity, concentration, dilutions. Those are really important things. As I mentioned before, being able to write actual equations, understanding, if I just have reactants, what am I going to get on the product side? A lot of what you will be given in this class and a lot of the chapters will not be equations. They'll just be things in words like, hey, you put this and this together. You need to figure out what happens on the other end of the arrow there. And it has to be done not only for points, but it helps with the actual calculation part. So you need to be able to do that. So definitely want to review reactions, solutions, concentrations, basic molar maths, figuring out how much to weigh out for things like lab, if you're given the molarity and how much volume, how many grams and all that type of stuff. So up on Canvas are some review modules of some of the first semester stuff that goes over some of these things. This stuff will be posted this lecture. Any questions on any of that stuff?